Good afternoon, everyone. Welcome to the Design of Reinforced Concrete Structures Problem Solving Session. It's week 11 today, and we will be discussing a design problem related to torsion. Last week, we also discussed a problem related to torsion, but there we only checked the adequacy of a section that was given already. Today, we will be designing the reinforcement as per the codal provisions for the given loading on the given section. So, let me start today's section. As in week 11 in the online lectures that has been posted on the website, the torsion lectures are still going on. Week 11, it's designed for torsion. Lecture 27A and lecture 28A, both are discussing about the torsion. So I thought it will be better to give more insights about it in today's lecture as well. So in today's lecture, we will be designing a problem in which a rectangular we are given a rectangular beam. Rectangular beam were given a dimensions of 350 mm wide, 350 mm wide, and 750 mm as overall depth. 750 mm overall depth. And it is subjected to an ultimate twisting moment of mt is equal to 140 kilonewton meter, and it is combined with an ultimate hogging bending moment. Ultimate hogging moment acting on it is 200 kilonewton meter, and ultimate shear force acting on it V is given as 110 kilonewton, and we are using M25 grade concrete and Fe415 steel. This is the information that has been provided. We have to design our section reinforcement for our given section under these loading conditions. A twisting moment of 140 kilonewton meter, a hogging moment of 200 kilonewton meter, and an ultimate shear force of 110 kilonewton. So from the design given loadings that have been given, from that we will deduce the equivalent moment and equivalent shear force acting on our section. From equivalent shear force, we will uh, deduce the equivalent shear stress acting on our section, and that shear stress we will be using for designing of our either shear reinforcement and torsional reinforcement, because that will give us the idea whether the stirrups design will be governed by shear or it will be governed by the torsion. And this hogging will be used in reducing the equivalent bending moments for the design of the flexural reinforcement. So first we will start with the longitudinal reinforcement, design of longitudinal reinforcement. Longitudinal reinforcement. So in that part, first we will calculate. It is a similar process we have to follow. The last problem we did for the checking the adequacy, same steps we have to follow. But here, the only one thing we have to do is to give the reinforcement. Reinforcement was already given at that time. One thing we will assume here is one thing we will assume we'll assume moderate exposure conditions, mild exposure conditions. Mild exposure conditions, and from code we can see that for mild exposure conditions we can have a minimum cover of 20 mm. Okay, 20 mm. So we will assume effective cover to be 50 mm, so that our effective depth d equals d minus effective cover. It turns out to be 750 minus 50, which equals 700 mm. Okay, So we have reduced our, for example, I am placing my reinforcement here. So I have reduced, sorry, for time being we have measured the effective depth. Okay, later it may change based on the design requirements. But for time being, we have put our effective depth as this one, 700. Okay, we have put this as 700, and this one comes out to be 50. Okay, these things are clear to you up to this point. So first step will be the design of the longitudinal reinforcement. In that, we have to see the effective bending moment coming on our section. Effective bending moment calculation. Calculation. So as per the code formula, the effective bending moment when the torsion is also present is equal to Tu1 plus d by b divided by 1.7. Actually, this formula is for the torsional moment. Torsional moment. So plugging the value, because we are given, sorry, I wrote it pair notations wrong. We are Tu. This is twisting moment. Okay. This is Tu is 140 kilonewton meter. Mu, M hogging. Mu is 200 and Vu is 110. Okay. This is simple. Huh? Mt will be equal to, we will write it as 140 times 1 plus overall depth is 750. Okay. Width is 350. 1.7. Okay. When we calculate this, our torsional moment comes out to be 259 kilonewton meter. Here we can see that torsional moment is more than the hogging moment that comes. So there is a lot of torsion acting on our section. So maybe the shear stirrup design will be governed by the torsion alone. So let us check further. Now we will see the equivalent bending moment. This is bending moment due to torsion. Now we will see bending moment due to torsion plus hogging moment that is already given. Okay. So for that equivalent bending moment, code has given the formula either torsional moment mt plus minus mu. Okay. So we will check both the scenarios. Mt is 259 plus minus 200. So we will get two scenarios. In one scenario, we will getting 459 kilonewton meter. Okay. 59 kilonewton meter. Okay. So this will be flexural tension at top. Okay, flexural tension. Because why this comes 459 kilonewton meter? Uh, yeah, the beam was already subjected to hogging moment. So as you already know, due to hogging, there will be tension at the top and compression at the bottom. But what happened is to this 200 kilonewton meter, an hogging moment of 259 kilonewton meter got added to it. So there will be a total flexural tension of 459 kilonewton meter at the top. And at the bottom, we have to deduct this mu because there will be sagging at the bottom. There will be compression at the bottom. So 259 was already there when we deducted that 200. So still there will be flexural tension at top. So if there was hogging moment on our beam section that led to flexural tension at top. So as if there would not have been any torsion, then the bottom would have been subject to compression. But as torsion is present, the bottom is also subjected to a little bit of tension. So 59 kilonewton meter effective moment will act at the bottom, and it will cause flexural tension at the bottom. Flexural tension at bottom. Just like this, for example, and this was beam section. It was subjected to this hogging moment. Okay. So this part will be in tension. This would have been in compression, but there was also torsion present. Torsion present like this torsion added to in such a way that the equivalent moment and the equivalent bending moment both caused flexural tension here as well. Equivalent, what was equivalent at the top? Flexural tension, and that was caused by a huge moment, 459 kilonewton meter. And at the bottom, it was compression. Now, when we calculated the equivalent quantities along with torsion, equivalent came out to be flexural tension as well. Flexural tension, and that was a little less than the top one, obviously, 59 kilonewton meter. Okay, this is just for the understanding. So we will calculate our these things. So we will calculate our dimensionless quantities, the parameters that you studied in the flexural design of the beam. So design of the top steel, design of top steel. We will calculate the factor R1. R1 is nothing. It is actually M equivalent to 1 ME1 divided by BD square. Okay. So we will take this as ME1, M equivalent 1. We will take this as M equivalent 2. Okay. Okay. We will calculate this as 459 kilonewton meter will be 10 power 6. Okay. Kilonewton meter, it will be Newton millimeter. Okay. Just keep in mind this is 350 and D is 700 whole square, and this will be millimeter, this will be millimeter square, it will be millimeter cube. Okay. And all are consistent, it will be 2.67 here millimeter, and millimeter cube goes, it will be square here, so it will be Newton per mm square will be megapascal. Okay, it is the unit of stress, megapascal. R1. Okay, 2.67. Now we will have to check whether this section is adequate in terms of carrying this moment, because we have to check whether this 459 kilonewton meter is less than its ultimate limiting moment or not. If it is not that, then we have to redesign the section, because we cannot cross the limiting moment capacity. Otherwise, we have to design it once again section, or to go for a doubly reinforced section. 2.67. So we will see whether R1 is less than MU limiting by BD square or not. Okay, so for this MU limiting by BD square, this depends upon the grade of concrete. We have MU limiting by BD square from code. You will directly get this ratio, MU limiting by BD square for FCK 25 and FE 415 steel. This ratio is equal from code equal to 0.1389. Okay, you have to follow the code. 0.1389. So mu limiting by BD square will be equal to into FCK. Sorry, it is FCK. It will be 0.1389 into 25. Okay, this value comes out to be 3.472 megapascal. Okay, you will see that this is greater than R1. So section is okay. Okay, so applying the formula for AST. The formula is PT. I hope everyone remembers this formula. PT is equal to AST by PT by 100 is equal to AST by BD. Okay. These formulas we discussed it in the initial lectures when I wrote these all formulas before starting the design problem for the design of the beams and flexure or the design of slabs. You are required to remember these formulas FCK by Fy. Okay. 1 minus square root of 4.598 R1 by FCK. Okay. When you plug in all the values for FCK, it will be 25. You don't have to worry about the units. I will tell you every dimension should be in mm and every stress value should be in megapascal. Then these formulas are valid. Okay, you can easily plug the values for megapascal and mm and forces in Newton. Twice 415 1 minus square root of 4.598 R1 we calculated above as 2 point. What is it? 2.7676676 divided by FCK is 25. Okay. So solving it, we will get PT by 100 as 0.866 10 to the power minus 2. Okay. So we have to see PT. How much AST will be? So AST will be AST. It is the required value. Okay. Remember required value. After that one we will assume that is the provided value. Okay. AST required is equal to 0.866. Hope you are following this. Required multiplied by the BD. B is 350 and D is 700. So when you calculate this, it comes out to be 2122 millimeter square. Okay. So we have to distribute this area between the number of the bars. So I am going with 228 diameter bars, 228.5 plus I am going with 225.5. Okay, I am giving total number of bars 4 at the top because it's highly tensile zone there. Fogging moment is acting and the torsion is also adding to this fogging moment. So if I see the AST provided from this combination, so let us calculate the AST provided from this combination comes out to be AST provided will be 2 number of bars in time is we go for pi by 4 28 square plus pi by 4 25 square. Okay, because we have 28 2 bars and 25 2 bars. Okay, everyone is will be able to understand this. So we will having 2214 square. Okay, square AST provided. Okay, for this combination. And now we will go for design of bottom scale. Bottom steel. Design of bottom steel. For design of bottom steel, we will calculate in the similar way R2. Okay, R2 will be equivalent to ME2 divided by BD square. Okay, so the values, plugging in all the values, it is 59 kilonewton meter. It will be 59 10 power 6 Newton mm. BD square is 350 mm times 700 mm square. Okay, this comes out to be 0.344 megapascals. Okay, everything is consistent. Therefore, PT required will be PT required divided by 100 will be equal to same, applying the same formula, FCK divided by 2 FY. Let me write FCK divided by 2 FY square root of, we have square root of, sorry, we have square root of 1 minus. Okay, we have square root of 1 minus 1 minus 4.598 2 divided by FCK. Okay, plugging on all the values, 25 divided by 2 into 415 times 1 minus square root of 1 minus 4.598 R2 is 0.0, sorry, R2 is 0.344, everything is inside square root, or divide by FCK is 25, but close. When we calculate this value, this comes out to be 0.097 into 10 power minus 2. This is very low steel percentage. Very low steel percentage we are requiring. So we have to go for the minimum one. We cannot go below the minimum one. So we are providing the minimum reinforcement. So code gives you the provide minimum reinforcement. Okay. So what is the codal provision for the minimum reinforcement? Code says that AST minimum divided by BD. Remember this formula. AST minimum divided by the BD should be equal to 0.85 divided by Fi. Okay. This is the formula. Fi. So plugging in all the values, 0.85. Fi is 415. So minimum percentage is 0.205 10 to the power minus 2. If you look how much this value was lower than the minimum value. So we have to go with the minimum one. Very low. Okay. So I am going with provide 316 5 bars. Okay. 16 bars. So AST provided, I am having AST provided as 3 into pi by 4. D square is 16 square. This comes out to be 603 square bottom. Huh? Okay. This comes out to be bottom steel. And what was our top steel? Our top steel was provide to. Okay. So another one is side face reinforcement. Since you are seeing that the depth of the beam is very huge, 750 so we have to look out for the side reinforcement requirements. Okay, side reinforcement. For side reinforcement, as you see that the overall depth is greater than 450 Code says that if the depth of the beam exceeds 450 side face reinforcement for torsion is required. Side face reinforcement for torsion is required. Okay, so for that AST required formula given by the code, AST required is equal to, it is actually 0.001 of BED. Okay, how much it is? It is approximately 0.1%, 0.1% of the gross area. Okay, 0.001 times 350 times 750. 750, this comes out to be 263 square. 263 square. So I'm going with provide by providing four 10 mm bars. Okay, 10 diameter bars. So what I gave is the provided was 4 bars into 5 by 4 into 10 square. Okay, this comes out to be 452 square. Okay. Mm, I will have this one. Actually, this will be, sorry, this is 314. Okay, 314 square. Okay. So we provided this value, side face reinforcement. Okay. Now we are going to, so we are finished with the longitudinal reinforcement. Now we have to go to the transverse reinforcement. Design of transverse reinforcement. Okay. So let's look up into this section. What's there? So in the previous class, I also told you for transverse reinforcement, when the torsion is present, we have to go for the equivalent nominal shear. Equivalent nominal shear as per code is tau V equivalent is equal to VU plus 1.6 TU by B divided by BD. Okay. So when we plug all the values, equivalent ultimate shear acting on our section is 110 kilonewton. Okay, already given into 10 power 3. Okay, plus 1.6 twisting moment acting on it is 140 kilonewton meter. Okay, kilonewton is 10 power 6. Okay, be consistent with the units. Otherwise, you will end up getting wrong values. Given by divided by 350 millimeter. Whole divided by BD. B is 350 and D is 750. Okay, sorry, D is 700. Okay, when you calculate this value is tau V equivalent is 3.06 megapascal. Okay, now you have a work to do here. You have to check it with, you have to compare it with the maximum shear strength of the concrete. Since we have FCK equals 25, so tau C maximum shear strength of the concrete is given as 0.7 on root FCK. That's the formula, the code FCK. So this comes out to be 3.1 megapascal. You have to compare, since tau V equivalent is less than tau C max, section is okay. Section is okay. What if tau V it was greater than tau C max? So in that case, you have to redesign the section already given, that is 350 divided by 700 You have to redesign that. Okay. So now we have to go check the shear strength of the concrete. First, we have to calculate PT, how much percentage of the tensile reinforcement we have provided. PT we have provided as, we provided 2214. Look here, 2214. We provided 2214. Okay, 2214. 2214 times 100 divided by BD. B is 350. D is 700. Okay. So when you calculate this is 0.904. So when you look in the table from the code, under the column FCK is equal to 25, you will find out that tau C, shear strength of the concrete, is 0.618. I have shown you this table many times whenever I have done a design problem here. Let me show you here again. Shear. This this table, our FCK is 25. Look into this column, and our PT is zero point 0.9. Look here, you will get your value somewhere here. What value we have taken? 0.618. You will see we have taken approximately like that one. 1 second. I will erase this. Just we will do this exercise once again. Look here. Our PT value, it's zero point 0.9 something. Our PT value 0.904. 0.904 approximately zero point 0.9. Okay, here, and M25 concrete given here. Check this value, this column, check this column. Where they intersect, take that value. Okay, you have to take this value 0.616. Okay, 0.616, check 0.616 value. If it lies between zero point 0.9 or one value PT, you have to interpolate between these two values. Hope you got this thing. Okay, so I have taken tau C as 0.618 megapascal. So now we are seeing here equivalent nominal shear. Tau V equivalent is greater than shear strength of the concrete. That is, shear is coming at that much high level that it is beyond the shear strength of the concrete. So concrete will no longer be able to tolerate that amount of shear. So it will crack. In order to prevent that cracking of our concrete, we have to give shear reinforcement and torsional reinforcement. Now, since here the torsion is very huge, so the torsional reinforcement shear stirrup design will be governed by the torsion. Okay, transverse reinforcement required. Okay, so let's assume first. We will assume 10 diameter two-legged stirrups. Two-legged stirrups. Okay, I will tell you a cheat code here. What you can do here. For example, we have to now find the transverse reinforcement. Now, the formulas are from the code are given. They include both. They include spacing of the transverse reinforcement, spacing SC, and they also include the area of the stirrups, ASP. Okay, ASP. Now, these are the two parameters that are both unknown, and you have one equation. From one equation, you cannot get the both parameters. So from two equation, from these two parameters, at least you have to assume one. For example, if you assume the spacing of the stirrup, then you will get the required ASP. And or if you assume the area of the stirrup, you will get the required spacing, and then optimize it as per the formulas given in the code. So better option is to assume the ASP, because we are having the options. Either we can assume 8 diameter two-legged stirrups, or we can assume 10 diameter two-legged stirrups, because we know the diameter of the bars. From that we can get the spacing. If we assume any random spacing and get the areas, maybe we will get that area on in which we will not, any diameter will not be falling. So it is better to assume the area of the stirrups, that is by assuming the diameter of the stirrups and the number of the legs, and getting the spacing, and then optimizing it as per the code requirements. Okay, so that's why I'm seeing here assuming 10 5 two-legged stirrups. So from this one, what will be getting the area of stirrups? ASVS. So since it is two-legged, it will be plus 2. Then it will be pi by 4. It will be d square 10 square. Okay. ASV will be 157 mm square. Okay, 157 mm square. So if we apply the code formula SV required, then will be. That's why I told you this SV spacing and ASV area of the stirrups is only related by only one formula given by the code. So in order to find one, we have to assume another one. Okay, ASV times D1 0.87 FY divided by TU divided by B1 plus VU divided by 2.5. Okay, this is the formula from the code. Okay, since we are having an effective cover, I already told effective cover. Effective cover we assumed as 50 mm. And in the last lecture, I told you in detail what are these D1 and B1. These are actually distance between the centroids or of the extreme longitudinal reinforcement. Extreme longitudinal bars that we have provided. What is the distance between their centroids? That is the D1 in depth direction, and that is the D1 in the breadth direction. So it will be easily calculated. D1 is equal to 750, deducting the effective cover from both sides is 50 times 2. Okay, same will be B1. B1 will be 3 overall breadth minus effective cover times 2. So we will be getting 650 and 250 respectively. Okay, these are the values. So when I plug both of these values here, I will get SV required as ASV is here. Plug the ASV from here. P1 D1 we calculated. Plug the TU as 140. Okay, I'm not writing it again. 140 and B1 D1 everything is calculated. So when you calculate this, it comes out to be 61.0 mm. This is very low spacing. If you provide this much of spacing, what happens is that this stirrups will get congested. So we'll have to look for another alternative. You have to go for the higher diameter of the this. I mean to say that stirrups very low. So going increasing the diameter, we are providing. Look, this design process is all about the iterations. You do one iteration using one ASV, you got some spacing, but that spacing was too low that it might congest the section reinforcement in the beam, and you won't be able to pour the concrete in it. So you have to do the iterations all the time until you get the perfect spacings that are as per the codal requirements, that are above the minimum value and below the maximum values. Providing 12 diameter two-legged stirrups. Stirrups. ASV will be equal to pi by 4 into 12 square into it is two-legged. It will be 226 square. Okay. So SV required will be here. SV required is the same formula. So SV required will be we will directly plug the values. ASV is 226 into D1 is 650 into 0.87 into 415 divided by it is 140 into 10 power 6. B1 is 250 plus VU is 110 into 10 power 3 divided by 2.5. Okay, when you calculate this value, SV required comes out to be 87.8, somewhat a little higher value from the earlier one. Okay, required. Uh, Here it is spacing and area of the this. I mean to say that area of the stirrup is inversely proportional to each other, roughly inversely. So for example, here I was getting very low spacing that it might congest the reinforcement. So I go for the higher reinforcement that is higher diameter 12 pi. That's why it's reverse of the two. So SV required is this one. Okay. Now we have to check the minimum spacing requirements from the code. I told you it should be above the minimum and below the maximum spacing requirements. So code says that SV should be less or equal to either x1. Hope you all remember what are the definitions of x1 and y1. X1 y1 divided by 4 or 250 mm. X1 earlier B1 and D1 were for the from the centroids of the longitudinal reinforcement. Now X1 Y1 are the distances from the centroids of the stirrups uh, in breadth direction and the depth direction. So X1 will be 250 already that B1 we got, plus we have to add the diameter of the one bar that is 28, and we have to add half the diameter of the we have to add half the diameter of the bar from both the sides. That will be the one diameter of the stirrup that is 12. It is equal to 90 mm. Okay, and same with the Y1, 290 plus 650 plus 34. You have to calculate these things yourself. This is very easy. I have told it in detail last lecture. 243 mm. Okay, 250 mm. So or it was 300 mm. Sorry, 300 mm. So we have to check all the values. These are the minimum values. Okay, minimum values of the spacings, and we are getting 87. We were getting 87. So we will give the minimum of all the three. We will provide 12 phi two-legged stirrups at 85 mm center to center. Okay, sorry, I wrote it here wrong. Pardon me. I was thinking it differently. It's very low here. From the formula, you can itself see it. Spacing required is directly proportional to the area of the stirrup. So I was having low area of the stirrup. That is why I was getting very low spacing. So when I increased the area of the stirrup here 12 mm to two-legged stirrup, I get the spacing little bit higher. So spacing is directly proportional to area of stirrup. Okay. Earlier I wrote it wrong. Sorry for that one. Okay, this one. So coming back. So we are finishing our design problem. So we provided this stirrup tower section. This was everything. So let us sketch the detail what we provided. Okay. So firstly, we'll go with our section. This is our section already given. Okay. Then we have to provide 28 5 bars. First, I will draw the stirrup. I will draw the stirrup like this one. Okay, this is our stirrup, and we are going with this is our one bar. This one bar. I am showing it with color coding. Okay. This one I will write later. No, right. This is 228 5 bar. Okay. Then we have provided 225 bars. Okay. We have provided 225 bars. Okay. And we'll go with the color coding as 225 bars. Okay. At below we provided 316. Okay. 316.5. Okay. One here, one at the extreme, and one at the middle. Okay. Let me write this coding as 316.5. Okay. We've also provided the side reinforcement. We provided 4 bars, two from each side. We will provide one here, another here, one here, another here, and this coding is these are 4 number bars, 10 5 in diameter. Okay. And we will write the dimensions. This was 350, 350 mm. This is overall 750, 750, and this is 50. So our effective depth comes out to be 700. Effective cover is this one, so this comes out to be 700. Okay. 350, 410. This is 350 also. This is required design section. Design section. Required design section for this loading. Okay. Required design section for this loading. Okay. Okay. This one. Okay. So we completed the torsion and we discussed one detailed problem in which moment was also coming, torsion twisting moment was also coming, and shear was also coming. This is one of the detailed problems you can solve in the torsion of a beam. So we were already given a section with the grade of steel, grade of concrete, and loading. For that, we designed the longitudinal reinforcement at the top, at the bottom, and side reinforcement as well. Designed the cover requirements, and after that, we go for the shear reinforcement, including the torsional effects as well. Thank you everyone for joining this session. This is all for today.
Hello, sir. Hello, sir.
Yes, yes,
Sir, I have asked. Sir, I have a question, sir.
yes, yes.
Is it exam is subjective or objective, sir?
I don't know about that one that you have to post in the NAPTEL site because I'm not concerned with your exam. I'm just to your TA for problem solving session. I'm not the main concerned TA for that one.
So is there any platform to drop a message?
I don't know about that. Maybe you can contact the NAPTEL team.
Okay, sir. Thank you, sir.
Okay, thank you. Thank you everyone.